The upcoming talk is titled "How AI Engineering Addresses Sense-Making, Reasoning, and Explainability," presented by Dr. Mark Stefik. And this paper has received the Frontier Science Award in the section of robotic science and systems. Now let's warmly welcome Dr. Stefik to present his talk.
I am so pleased to be here, and I thank you all for finding your way through the maze, through all the different buildings here. 15 parallel sessions, and you came to this one, and I'm thankful. My joke might have been I would be so glad my wife was here to watch me, but in fact, now I have you guys as captives, and what I have to tell you in the next hour makes this worthwhile to you and gives you some things to remember. So first, a word about this title, because you don't often see an AI talk which uses a word like sense-making or puts it in the same breath as reasoning and so on. So the thesis, this talk is really about AI engineering, but before that, there's AI research. It has been striking over the last decade or more how fast AI is moving. And in fact, where I sit, which is in the Bay Area, which we always think is the center of the world, but I think I was at the Forbidden City yesterday, and I may have to revise my geography because of where we are in Beijing. But if you drive down the highway from Stanford University, which is close to where we live, to San Francisco, along the highway, you'll see billboard after billboard after billboard, great signs saying C3AI, saying not saying Glean, saying Distill, saying all these companies that offer businesses make your business become modern, use AI. And in fact, there is this sort of land rush going on right now with around AI, as I'm sure everyone in the room is seeing. And it would seem that there was a great discovery, and now there's huge investments. There's NVIDIA is a $4 trillion company, so even more in yuan, of course. And so there's certainly a lot of excitement. And what was striking to me, because many of my friends are in small startup companies who are trying to use AI for various things, and their story about using it doesn't line up exactly with what the billboards would say. And if you look at the statistics in the United States about companies and their adoption of AI, they're enthusiastically investing in it. Are they making products that use it? Are they using it to streamline their businesses and make them modern? In fact, only a very small percentage of them are succeeding at doing that. This was a puzzle to me. And so as I was moving from my previous project, which was the one that was the paper was about, so the award-winning paper was about explainable AI. I thought I would try to find out, well, why are these systems still not explainable? How do they work? What are their faults? Where are they strong? In fact, how do they work? So this talk is actually going to be a bit of a tour of that. I'll go to the first slide. We might think at the beginning of the current crop of AI enthusiasm is happening at a conference in Florence, Italy, where a computer vision program took best in show. And this is a quote from Fei Li, who is she's at Stanford now, but she was at that conference. And I just imagine if something like this would happen at this conference, as she said, arriving at the room, maybe not so different from this room, word had spread by the next morning something historic was going to happen. And then they watched as a program written with machine learning dominated all the symbolic-based AI programs. And she said, we realized that the field was changing. It was going to be unifying under a new banner, the banner of machine learning, which changes our relationship to the machine. It's no longer just how we programmed it. We are expecting the machine to learn on its own and do things we might not have been able to. So I take that as being like the the Big Bang of AI starting. But then what happens? Well, deep learning was exciting. There were game playing programs famously working in it and so on. Not many businesses were using it, and every AI seemed to be a different recipe in terms of how you might build the neural network. And was there a way of creating many commercially viable systems for all these businesses which might have the money to do it? Well, the next thing that happens is really quite a few years later. So this is history as I see it, calling out what I will say were the breakthroughs of the last little bit and how they work and what they don't do. So this is the transformer model. If I could just ask, how many people here are familiar with transformers already? Yes, no, maybe. Okay, well, so I can't tell you the depth of what a transformer model is, but I'll just say there's a computer system where there's an encoder which is taking in the data in vector form, and it takes input tokens, embeds them from those vectors. There's a decoder which is going through essentially a classification and computational process on those, making output tokens. And then the key, but probably the key invention here was self-supervised learning. If we go back to the program that was important at the computer vision process, there were 30,000 data points which we used to train it. A really big number, they thought, which is dwarfed by the size of the things we're doing today, of course. And it was very expensive to do all that supervised learning. And so self-supervised learning meant that the system could learn on its own. It could find patterns in the data to drive it to the next step. So I take that as being the next breakthrough along the way. Shortly after that, 2019, along comes BERT, this bidirectional encoder. What was interesting about BERT, it was based on the transformer model. So it's standing on top of this system, which learns by itself by grinding through the data. But what data? Well, the data that was most available, the thing that BERT found that allowed it to train so much, was the availability of natural language. So it would do self-based learning on that. Now that pattern of the idea of using the abundant text that was on the internet shaped the vector of where AI was going to go. It wasn't learning about the world. It was learning essentially how to predict things that people say. But it was really exciting. So, but it goes on. The land rush was beginning in San Francisco. This land rush was taken by the fact that all the people who had left the city during COVID were streaming back into San Francisco to join startup companies. NVIDIA was building bigger and bigger chips. Much more investment was going on, and things like BERT were impressive because people could sit. They said, "Look what it's doing." So we will take a look at what it's doing. But that's a. But one of the things with BERT, and maybe I should go back and comment on that. An important thing about BERT. Why was it important? It's because if you went through all this training process to build what we now call a foundation model, and then the output tokens from the transformer would be for whatever application you had in mind. Maybe it was machine translation. Maybe it was some other linguistic processing. But if you wanted to do something different, you started all over again. Take all that training data, all those machines, all that electricity, and build another model. What BERT said was the idea in what used to be called transfer learning, which is if you learn a lot about one domain, some of what you learn from that can be used for another domain. And so BERT was really the first program that succeeded on transfer learning and doing that. That I think was a piece of what triggered some of that excitement. Another thing that came along then, which I think was a big surprise, was the idea of few-shot learners. Are people here familiar with few-shot learning? Looking for maybe hands. Maybe it's impossible to raise your hand in this culture, but I'm pretty sure that many of you, it means that you learn from a few examples, just like you do. And so if you were going to use the fine-tuning, which was the idea used inside BERT, to go from one model to another model, that still took at least 10,000 or more examples to trigger over to the second application. But with few-shot learning, it takes a much smaller number. Now that was starting to get exciting. There was a science paper by Josh Tenenbaum, a cognitive psychologist, in Massachusetts who wrote a famous paper in Science in 2011. He said, we don't understand how it is that children learn so much from so few examples. That's in fact where the few shot learning phrase comes from. It was from that question he asked psychologists. He said, they seem to learn so much from so little data. How can that be? And then, raises his hand like discovery was, if they've learned the information they need must be coming from somewhere else. And so in the case of something like BERT, it is coming from that foundation model, and then you're using enough to train it to do a second application. So this showed that when you have something like that kind of training, the material used in the context, which goes into the machine, basically you could think of using those as instructions for how to do things. Um, uh, Whereas fine tuning would take 10K examples with the approach that was discovered in this paper by Brown et al. In context learning, took it down to a few examples. Now that was getting exciting. We're now looking at something which not only can learn something deeply, more or less on its own, it doesn't have to be supervised learning. It's self-directed learning, and it doesn't have to be a transfer learning process where you're doing you're modifying the weights to build a model that can do a second application. Now you're keeping those weights all the same. You just have a few training examples and off you go. So there was one more little invention that came along here called RAG. And this, of course, retrieval augmented generation. The idea here was, of course, that the system that's learning to do something, if you have a business, and let's say you have a business that's managing supply chains, I was surprised to know in talking to my friends who are in these sorts of businesses, that in a large company, I'll just pick one at random, like Lenovo, which makes laptops. Some of you may be using a Lenovo laptop. They're trying to manage the supply chain. They have thousands of interruptions in the supply chain every day. And getting on the phone to say, how can we get that part? Where else can we get it? Have we gotten a part from that company before? Was becoming an enormous bottleneck in the company. But where could they find the information to address those things much more automatically? Who to call? Who are our last customers? You're not going to get that by reading random data on the internet. So what you wanted to do was to use more training data, in this case, company records, the memos, all the information you had before, which told you what was going on. So this is what RAG really came about for, was to allow an organization to augment this large model that was pre-trained using this in-context learning and feeding it their personal private information, which couldn't be found elsewhere. So then came the next commercial explosion, which got everybody excited. And I think one of the important lessons, so what happened? What's so exciting about it? Well, as it says here, they released a prototype. Users were surprised by how natural it seemed, a conversational dialogue. I imagine there's nobody in the room who hasn't used ChatGTP or one of its variants or one of the ones that are DeepSeek or something from here. But in this case, the first one that was that good, there were 100 million users in 2 months, the fastest growing consumer product ever. So companies like Google woke up the next morning and said, we're in trouble. This is better than search. Our business, you can do this, but you can't put advertisements on it. People are getting information very quickly. Over the next few months, thousands of people were fired in the Bay Area who were working on the wrong part of AI or the wrong part of the business. And everybody started focusing on making language models better. So this is happening all over the Bay Area. Little companies have been doing this thing, and I imagine it's happening here in much the same way. So this was a kind of a wake-up call of a sort. Meanwhile, there was a pesky person working at Google named Bender, who I think Elizabeth Bender, I think is her name. And she said, these things are dangerous. They don't, and I'm not talking, there are many dangers with AI that this talk is not about. I'm not talking about bias. I'm not talking about making weapons. I'm talking about AIs that just don't know what they're talking about. And she said, these are like parrots. She coined the phrase stochastic parrot to characterize how it is these models work. And these models work, as probably many of you know from the transformer model and what was done before, they take sentences that people have used, sometimes from different contexts, and compute what is the most likely thing, the most likely next word that would be said, and it generates things. So in the enthusiasm for, so when, the story behind this paper was when she was a famous researcher there. Um, and in the US, sometimes people of different races feel they have difficulty getting promotions and so on. She was a big deal. I think she's a black woman, but I'm not sure. She had a potent research group, and she had this paper that was accepted saying these models that we're all about to build are dangerous because they don't tell the whole thing. If you have a business, let's say it's doing healthcare records to pick something sensitive, um, and you're trying to give an accounting of what's wrong with the patient or what the diagnosis should be, and it's making stuff up. That's really unacceptable. You have to have an AI which tells the truth, and this one doesn't know when it tells the truth. Famous story in the U.S. And I'm sure this has happened lots of times. An attorney, he didn't know much about AI. His kids all told him, use this wonderful system. And he had a court case coming up the next few days. Used the system, prepared his court case, went before the judge, had, many references, cases, things like that he was citing. He almost lost his license. The cases didn't exist. The judgments didn't exist. His case was complete hogwash because he'd used it based on what ChatGPT 3.5 told him. So this worry was real. Google didn't like hearing about it. You can read about her and what happened, but Stochastic Parrots is now a very well-known paper among the people who have things to say. Well, so I want to say, yes, it's true that these systems, for the most part, can do a lot of things wrong, and yet they can be terribly useful. I start by just giving you an example of one. I should have had some pictures here, but you maybe use your imagination. So my neighbor was outside doing something in the yard. He came by and said, look, my new house, we're getting a roof on it. He said, look at these things. He had these plastic 3D printed tiles that he was going to use on his roof. He formerly, before that, had a wood shake roof. What is my house going to look like with these tiles? So he's using a version of ChatGPT with the visual generation, the language generation, all that. Gave it a picture of the house, gave it the product brochure for the tiles, and what will my house look like? And it made a picture. It looked a great deal like his house, but with the correct roof tiles on it. It was amazing. So obviously what's going on here is deeply exciting and wonderful, and AI systems could not have done that before. But if you look at the house carefully, it lost a window on the second floor. The window panes on the first floor were all messed up. In other words, but for him, that was okay. He just wanted to get a sense of what his house would look like. So with a human in the loop, he got some great value from this. And what I'm going to say in the next little piece is under what kinds of systems what kinds of problems are LLMs really a great gift. So one more paper I want to cite here. This is also a paper in Science by Alison Gopnik and some of her colleagues, and Farrell and some others. She says, we are misunderstanding what these programs are, these LLMs, and what they're good for. She says, we should not think of them as being intelligent because they make such silly mistakes. That's hardly intelligent. But but they do a lot of the things exactly right. They're a new kind of technology that allow us to share information that other people have written. You got to check it. You got to see if those references really exist. You have to bring some kind of common sense to regulate what it is the system said before you just believe it. But if you do that, it's terrific. And I want to say it really is quite wonderful, especially when the number of errors is small. Here's an example of a project I did a very long time ago, right after 9/11 happened in the US. So I was working at Park. We were working with the intelligence organizations in Washington, D.C. They were trying to track down terrorists, something which basically every country has to deal with. So it was the U.S., and I'm sure it's happening. There's worries about this in China. There's worries about this in Europe. So it happens everywhere. So we were working with the analysts, and they were being over flooded with the information they had to go through to try to track what's going on within. In that case, it was the Soviet Union and chemical warfare and biological warfare and things like that. So one of the things we did what's called a cognitive task analysis, which meant we followed the analysts around to see exactly what they do, how they think, what stages do they go through. This is a little map of that thing, and I don't want to go through it all in detail here, but what they're gathering data, they're creating a pile of evidence, Then they form these schemas of what they think is happening, little representations of the world from which they were going to make their conclusions. They form hypotheses, they test them, and so on. But in doing this process of gathering and reorganizing and repurposing the information, 90% of the time they were doing information foraging. In other words, they spent most of their time looking for the information, far less than 10% of the time actually analyzing it. This was a big surprise. But guess what? If you have an LLM, that's exactly what it's good for. These things are dynamite as being good sense-making tools. So many of the businesses, when they're going to get a value out of using this part of the AI technology, are likely to get something good. Okay, I did an experiment with Perplexity, which is one of my favorite of the LLMs. I asked the question. I said, Perplexity, explain to me AlphaFold. So AlphaFold, if you folks don't know what it is the creators of it at Google won a Nobel Prize. It addressed the protein folding problem. And in this, I went to a climate talk in this room an hour ago. It uses the generative AI, deep learning techniques, and so on, and compared some proteins or whose structure was unknown with proteins whose structure was known with various data to make predictions about the structure of the protein that was unknown. How does this work, Perplexity? One day I asked Perplexity and it gave me this answer. The next day I asked and it gave me this answer. And the answers are both mostly right. One of them doesn't bother mentioning what the breakthrough was inside this. Another one overstates things a little bit. And I noticed there were some small errors in it. So, and they weren't consistent between the two different reports. So I did a trick. I said, Perplexity, tell me what is wrong with your last analysis. And by gosh, it sounds like you're talking to a smart colleague. Perplexity says, well, my earlier report overstates universality and accuracy. It does this thing. It ignores environmental and molecular context. By and large, it was correctly saying things that were wrong in the first report. I said, but how did it do it? As it turns out, it wasn't analyzing what it did at all. When the first news reports came out about AlphaFold, a lot of things were said that were overstated. And then other people wrote down and said, that's not right. This is what Perplexity really did. So they're laying out all the things that were wrong in the reporting about Perplexity, or about AlphaFold. What Perplexity did is what Perplexity always does. It went out and looked for documents criticizing the early news, found reports by people who criticized it, and then this report here doesn't mean it understood a darn thing about what AlphaFold did. It meant it found another report and copied that. So now that was an interesting thing because we imagine having AIs that could be our scientific colleagues and could do reports for us, but we would presume they would do this from analyzing from first principles, from doing experiments, from combining theory from things they already know, and that's not what LLMs do. So you can see there are some limits in terms of that thing, and one of the things so I'm now moving to the second part of the talk. I said this is going to be about sense making and reasoning and explanation. So what I'm saying so far is it's pretty good with sense making as long as there's a human in the loop, because of what it does is not grounded in real models of the world. And we'll come back to that. Okay, so when do you need reasoning? Well, if you have an AI application, let's say it's one that's regulated by the government, like drug design or something like that, there turns out to be a very low tolerance for error. So you would like a system which actually reasons from a validated model of the world in some way. It may have to satisfy regulatory requirements, like if it's making, let's say it's the system might be for getting a loan for your house, or it might be for what drugs you should be paid for in your medical plan, or something like that. Goofy responses, not satisfactory. Other places where there's a lot of reasoning required, if you've got a scheduling problem, a design problem, manufacturing problem, construction problem, logistics, it goes on and on. And probably most of the scientific applications that we're hearing so much about at this conference would fall into this kind of a category. You have to have a reasoning system inside there somehow. So let's look at what the current crop of AI systems being advertised on highways in the Bay Area are doing. Well, they have three approaches. I mean, and I'm using big categories here. One approach is called, I'll call approximating reasoning with prompt patterns. In other words, just like we saw with context learning, you could cause the system to do something interesting or form a reason or make you report in a certain way. You try to make it reason better by giving it patterns from which it either might learn or follow or examples of how to do it. That's category one. Second one, another Nobel Prize, for Bartow and Sutton for reinforcement learning, which has been, which is also you can have deep reinforcement learning, as we'll come along to. So it can be a highly combinatorial process. It has its own limitations in terms of where the data has to come from and how much computation is needed. But that's another one. And then the third one, and this is the one that almost all the AI companies are using. They're saying everything has problems. We can't build perfect systems easily out of imperfect parts. And so we use different kinds of subsystems to do different things. So people are using agent models and things like that. They essentially are putting multiple kinds of reasoning or data fetching systems or retrieval systems, language production systems, which compensate in various ways for each other's mistakes. So that is an engineering discipline. It's not, it's, it's too messy to be satisfactory for a theoretician, but the engineers are faced with that because that's the only way they can build systems that will satisfy these customers within a narrow area. So the requirement for a narrow AI is it has to work fine on a limited domain. That's much easier than building one that works for a broad number of domains. And so the problem is more tractable. So let me go forward on these guys a little bit, just to say what's going on. Approximate reasoning with patterns. So there were a couple of fairly famous papers on this thing. Now we're getting up to 2023. Now, we're only talking 2 years ago, and these things were hot news. In fact, some of the guys who wrote the chain of thought paper worked for me in the past, so I knew them pretty well. And when I first was reading to try to catch up on what's going on, what they had done, I thought, "Gosh, this is smart." And congratulations, guys. So what it does is it tries to lay out the intermediate steps in reasoning to more or less constrain the language generation and get answers correctly. Before they did them, the first LLMs, if they were asked any questions involving arithmetic, were hopeless. They actually didn't know how to add or anything. And so the answers were just goofy, causing people, including children, to smile at how silly they were. So something like chain of thought helps, but even this requires that the system have a low level of more equivalences. They have to know something about what the words mean, or they can't even do that. Tree of thought is sort of the same idea, except now you've got multiple reasoning paths, and you pick the ones that's the most self-consistent. Wait a minute, Mark said self-consistent. Is that the same as consistency? Is that like a mathematical consistency? No, it almost has very little to do with that. Self-consistency, what it means is that most of the paths related to what came up with the same answer, the ones that were most within the same echo chamber, if I put it that way, were the ones thought to be most consistent. So these were the foundations on which the proximate reasoning with patterns were based. That's not good enough, by the way. So how about reinforcement learning? Well, now here we're on much sounder grounds. As long as you can have a model of the world which has high fidelity. So your sim to real correspondence has to be very good if you're going to make predictions to it. So this I just took from the textbook on reinforcement learning. It's about how to map situations to actions. There's a reward signal, which means you've got to have a way of characterizing the reward. There's going to be an issue around that for making the sort of self-learning systems. You pick the path or the plan of actions, which gets the greatest reward. I won't go into more about it. DRL is a wonderful extension of deep reinforcement learning is a wonderful extension of reinforcement learning because it gets to use a neural network to basically organize, to model the inputs better and also to give a more reliable model of the reward function. So if I want to sort of speak very simply, why is this different from what the LLMs are doing? RL models compute what to do, and the LLMs compute what to say. And they can compute it by what other people have said. A tiny segue about that. I don't know if any of you have. I don't see many people maybe old enough to have young kids. Maybe you have younger brothers and sisters, and so when they get to be 2 or 3, um, there's something they learn to do. So imagine, um, I'll have an imaginary friend here and we're playing some kind of a dodgeball game on the playground. And you're supposed to throw the ball and they're supposed to get out of the way and that sort of thing. If I say, just move over here, you'll be safe, my friend here's going to say, aha, he's trying to fool me. I can't trust him in the situation. So that my friend will have a model of when I'm telling the truth and when I'm not telling the truth, a teleological model of the other person. So it learns to tell what's true, what's false by comparing it to other things that it knows. LLMs don't do anything like that. And it's stretched to make the reinforcement learners have a model that's rich enough for that. So it's surprising that every one of you learned to do that by the time you were 2 or 3. Just keep that in mind as whether we think we have our approaches as good as they can be. Okay, so moving forward. Okay, more variations. These are 2 successful, useful versions of reinforcement learning. I'm not 33, 13, 31. I guess I'm not. I didn't want to get into these too much, but both of these have been important commercially in making the LLMs better. This one is trying to have human input. Only a slight problem with human input. Let's pick 4 or 5 people in here who are checking to see whether this thing that was generated is true or false or agreeable. We don't agree with each other necessarily. I mean, 2 different people can have 2 different feelings about something, or opinions about something. So what does it mean to be human aligned? So I mean, there's sort of fundamental issues there when we have different groups, different kinds of opinions, and so on. I'm sure we can find definitions of that will be satisfactory. But they've got a room full of people probably people online, remote working, checking boxes and saying true, false, and stuff like that to get the scale on correcting the kinds of errors that the LLMs are making. But doing that with reinforcement learning there's an algorithm there which I won't get into. Again, now we're getting close, 2017. So this is really only the last few years. And this other one here, which is getting at some of the principles that we probably should be using, it's about reinforcement learning with verifiable rewards. When you hear words like verifiable, you're getting into things like proof checking and logicians and stuff like that, which are systems that by themselves don't scale. What I want to say, because it may sound like I'm really negative about these things, but I'm not. I think that these are all moves in the right direction. I think there's some very foundational things that we need to make our AIs better. And some of the concepts here are probably going to work just fine. But the deeper problem, as I will come to it later if we have time at the end, is that we're not training our systems in the world. We're training them on what they can read. And that leaves them compromised in knowing what's up. Okay, compound systems. So some of my experience in working with this thing, I was visiting some of the sort of AI companies that are helping the businesses build systems, some of my friends who are running startups, and they are doing all kinds of tests. They will test each new version of of the large models from 4 or 5 of the major companies and try to use them in their companies. So this is from 2024. It's the group at Berkeley, and they're looking at the fact that we're trying to build perfect systems out of imperfect pieces, and then trying to build something which can check the outputs in some way. So this is where the compound systems come in. Notice that the theory behind these things is now getting messy. We have definitely moved from this pristine idea of a nice pure research project to an engineering project, which is just trying to make something work. And that's what's going on for most of these things. But the principles they're using may not be all that bad. I mean, but you have to have a way of combining different kinds of information and deciding how much of what to believe. So, so this was a prediction from the Berkeley group, just saying expect to see more of these things. And then this is from a friend of mine who runs a company in France, where he's using GenAI, in other words, the combinatorial generative AI systems. But then he wants to pair them up with old-fashioned AI, which is rule engines and so on, so that when it generates something, there's another program which can just check it and act and catch it. Now, what was wrong with the old symbolic systems was they didn't scale. It was too expensive to build them. And we can talk more about that probably I wrote a textbook on that, and then it's from a long time ago. But I mean, it was wonderful technology, but it was based on the idea that you would build systems depending on what people told you, and you're limited by how much you could build them. We weren't using machine learning at that time. So this business of building systems that learn by themselves or self-directed learning, that's a really important idea, but they have to be put in a space where they can actually have the right experiences. So this last quote here from Sanjay Mittal, he has a company, he's had several companies. In this case, his group was trying to look at building a program that could take orders at a restaurant. He wanted to work for any kind of a restaurant, so it would be takeout, it could be at the window. Basically, the program would have as its input a menu, and then it would be able, for example, to man the window, let's say a takeout food place, and take an order from a person. So there's lots of problems inside there, like the person gets halfway through the order, changes their mind. Maybe the menu is complicated. Maybe they order things that don't exist. So he was trying to do that using LLM technology, and absolutely with a crack team could not make it work. He previously had a symbolic version of it. This is not a highly combinatorial problem. It worked fine. But the investor said, you're not using the modern AI. So you really better get with it and use the new stuff. And so he launched with his team an analysis of building these things based on LLM technology. And I wondered Sanjay, I said, well, maybe the LLM is just fine, and you guys don't know how to write prompts. Of course, we're long enough friends that he knows I'm both pulling his leg, or that means joking with him, but also it's a challenge because it's what you write to your few-shot training as well as what it does before. But they did a very exhaustive effort with many teams trying to do this and could never get the error rate down. So his conclusion was that they would not be satisfactory. I may have a quote on that in the next slide. Well, no, I guess not. So, but this is not just his company. I've been having these conversations with maybe 3 or 4 companies right now, and talking to others who are in the business of building AI companies, so that serve business needs. So at the beginning, I said this is going to be about AI, meaning AI research, like basic research, like the conference is about, and then we have this technology which is very impressive. It's based on marvelous insights about math, about approximation theory, about neural networks. Really, the research has been outstanding, but it doesn't mean that our ambitions for building big, broad intelligence is close to being achieved yet. And so, and in the meanwhile, for those who can't wait for it to materialize, the AI engineering companies are coming up. And the stories I've given you today are essentially like war stories of the kinds of things that they're facing with. So what does this tell us about what we might think about as researchers for the next round of building AIs? So I'm going to give you some speculations of my own, how I think about it. It'd be interesting to hear from any of you who say that makes sense, that doesn't make sense. We could have a conversation different from the one that I had with Perplexity, when it didn't know anything. Maybe one where we might actually test our ideas. So one of the things I would say is that there's obviously many of the outstanding papers we've seen at this conference are partnered with researchers from different fields coming together. And so they might be using the AI basically as an approximation tool. That was largely true of the climate talk I was at before this talk. So they're using some of the underlying technology of building networks and building prediction systems. So this is to acknowledge that kind of work, and also the marvelous work on the math at the bottom of neural nets. And I'm seeing at places, certainly at Stanford and Berkeley, and a lot of this in Europe. I'm not as familiar with the work in China, but there's a sort of a virtual cycle where people who are in the neurosciences, people who design artificial networks, developmental psychology, and robotics are working together. And what they are finding is that when they build the models, they build a robot which does things like a child does it. They are every field is benefiting from it. The people who do the neuroscience work or do brain scanning, they can't really get a brain to do anything, but the psychologists can help them with that. So between the scanning technology and the experimental setups the cognitive psychologists do, the neuroscience people are getting something out of it. And that's true for every pair here. The groups like that are working together in organizations to do that. Um, and, uh, and when I look at what's going on there, and I imagine, I put on my playful hat about what I think I'd like robots to do, I sometimes, uh, um, I will say this to be provocative and not be exactly right, but to get the idea across quickly. There's a saying about people, which I'm going to misuse. It takes a village to raise a robot. So the idea here is to have robots that would go through a developmental sequence of ideas of learning things. So your kids, or in fact, each of us, we come into the world. Obviously, there's some things that are sort of built in. Evolution has already shaped it. There's things that we learn by the time we're a year old and 3 years old and so on. If you look at the developmental sequences that people go through, they map onto the same developmental sequences that animals go through, and whales and so on. It's really quite outstanding. I'll tell you something I probably come across, I'm not sure, as very formal, but I have a very juvenile sense of humor. And I was reading a book on child psychology, which the author was saying that we as parents often make a mistake in raising our children. We adult morphize them. Adult morphize meant we treat our kids as if they were little adults, but they're not little adults. In fact, sometimes she says they seem no smarter than the family pet. Now, that's a pretty bland statement, so it takes something strange like me to burst out laughing when I read that. But I had just read another research paper, and I'll tell you about that research paper. Maybe you will appreciate the humor of this. So this is the research paper where we're testing the sort of mental models of a child who cannot talk yet. And in this case, the child is set in front of a monitor, and events are happening. So there's a cartoon, for example, where you've got a character that's running along. It runs along. Now there's a cliff. They've run off the edge of the cliff, and they keep running. Of course, in this cartoon, they still are in the air. Then they look down, look horrified, and then fall. It's called, cartoon physics. Now, if you show that cartoon to a child who is 6 months old, they just stare at it. Nothing happens. If you show it to a child who's 9 months old, the eyes get big, it focuses, and they say something. The point being, you just got a probe into how much of real physics they've already learned. In other words, you couldn't ask the child what it knows about physics, but by watching its reaction to these things that do not happen in the real world, you just learned something about the sequence of things that they've learned. Now we're getting to the point where I thought this was funny. They did the same experiment on dogs. Same thing. So the dogs were going through the same sequence of learning to interpret visual imagery that people were. I think that's really fascinating. And there's a lot more to that story. If any of you are really curious about that, there's a long paper by me on arXiv on that subject about how we could possibly take those kinds of lessons and create create AIs in a different way. But this is me imagining what to do. It's got nothing to do with AI engineering right now, and it's not going to be reflected in the mainstream AI that we're seeing out there. But I suspect that things like this may become important as we try to go to the next level of making computers that think, perhaps computers that think like us and can help us understand the other guys. And I thank you for your attention.
Thank you, Dr. Stefik, for sharing his valuable work. Now we have some time for questions.
Okay. Thank you, Mark, for the fantastic talk. I really learned a lot from here. I just have a question, just a hypothetical question, because I'm also trying to discuss with some surgeons about using probably LLM for some more sophisticated surgery. Right. So for surgery, it is something that is very I mean, it's very important. So the tolerance for mistakes will be very, very low, right?
Exactly.
And as you mentioned, like LLM does have this kind of issues of making wrong statements, factually wrong things, right? So in that case, right, would you suggest that to improve this kind of interactions between like the surgeon and an LLM, right? So you listed 3 methods over here, for example, like reinforcement learning or compound AI agents, right? What would you suggest to make the interactions between the surgeon and the LLM more accurate? Yeah.
Well, I think the LLMs, by and large, will have difficulty being accurate unless there's something which checks what they do. The trouble is the way they generate sentences has nothing to do with the reality. It only has to do with what's been written before. Even if they are based on completely reliable material, but they combine material from different contexts, there's an issue that they will miss things there. I think it might be interesting to have, I'm just going to speculate here. I mean, if you're really trying to get the conversation to work right, it would be good to have a model which knows what's true, and then to use the LLM with that model to generate sentences to describe what's in it. In other words, I mean, this is that's a really good research question, and I suspect that you're not the only people who are wrestling with it. And I appreciate the fact that in these medical applications, not only does the conversation have to be valid and freewheeling so that you can ask pretty much anything, but you want to know that the system on the other side is using a reliable method to answer it. So it's not just a question of the language. It's a question of interpreting your question, testing it in some kind of a world, possibly a simulated world, a very detailed model, and then generating an answer. Or even more important, knowing when it doesn't know. So I hope that helps.
Okay, thank you.
Yeah.
Any other questions? Okay, if there is no more questions, now let's conclude this
Thank you.
talk. Yeah,
Good.
thank
Thank
you
you.
again, and
Thank you all for coming.
for attending this talk.